we shall discuss chemical shift and its measurement. Each proton in a molecule is in a slightly different chemical environment, and hence it does not have much difference in their resonance frequency. This difference is very little in comparison to the instrument field strength measured as 60 MHz. Therefore, it is very difficult to measure the exact frequency values of each proton accurately in NMR spectrum. However, the relative frequencies can be determined with more accuracy. For this reason, a reference compound is added to the sample and the resonance frequency of each proton is measured relative to the resonance frequency of the reference compound. Tetraethylsilane is the most commonly used compound as a reference. The position of various signals can be measured in terms of Hz by putting the TMS peak at 0 Hz. One of the characteristics is the position of the signal in NMR spectrum, called the chemical shift. In NMR spectroscopy, the chemical shift refers to the difference in resonance frequency of a nucleus in a molecule relative to a reference standard, tetraethylsilane, abbreviated as TMS, and is a key tool for structural analysis influenced by the nucleus electronic environment. Chemical shift is the position of a signal in an NMR spectrum, measured in parts per million, abbreviated as ppm, and denoted by the symbol delta. TMS is a common reference standard used in NMR, and it's set as del equals 0 ppm. The position of a signal, which is nothing but chemical shift, is directly related to the chemical environment of the nucleus, allowing us to identify different types of atoms and functional groups within the molecule. In MRI, the chemical shift imaging is a technique that uses chemical shifts to distinguish between different types of molecules or tissues in the same location. In different chemical environments, nuclei in a molecule absorb slightly different frequencies. The position of the signals in the spectrum is called the chemical shift. A chemical shift is defined as the difference in parts per billion between resonance frequency of observed proton to TMS hydrogen. So far, we have considered only the nucleus, but there will be some influence due to the electrons surrounded by the nucleus. Let us take an example of hydrogen atom subjected to a magnetic field. The negatively charged electron, which revolves around the nucleus in the presence of magnetic field, will create a local magnetic field opposite to the direction of external magnetic field. However, this local magnetic field is very less compared to the external magnetic field. This type of magnetic field is called as local diamagnetic shield. In addition, the created magnetic field is less than that of an external magnetic field. This is due to the shielding of surrounded electrons. Hence, the equation should be corrected bit. If there are more number of electrons, one can expect more shielding. Hence, the NMR signal will have some influence of existing of electrons. This change in frequency is calculated by chemical shift. But protons are surrounded by electrons that shield them from the external field. Circulating electrons can create an induced magnetic field that opposes the external magnetic field. The signal shift is very small, parts per million, but the great precession with which the frequencies can be measured permits the determination of chemical shift. The secondary field or local field either opposes or reinforces the external applied field. Therefore, the applied magnetic field has to change slightly to bring the nucleus into resonance. This variations in applied field and the effective field experienced by the proton is explained as chemical shift. The value of the shift depends upon the chemical environment of the proton. For example, aliphatic, aromatic, primary, secondary, and so on. When a nucleus of an atom is placed in a magnetic field, the electrons around the nucleus produces secondary magnetic field called induced magnetic field. If the applied magnetic field and induced magnetic field are in the same direction as shown in the figure, then it is termed as de-shielding. So this is your de-shielding. The external magnetic field and the induced, the external magnetic field and the local field, they are in the same direction. If the applied magnetic field and the induced magnetic field are in the opposite directions, then it is called shielding. The chemical environment around the proton is decided by the electrons present in the bond closer to the proton and the electrons present in neighboring bonds. These electrons induce their own magnetic field, which may reinforce or oppose the applied magnetic field. In order to occur NMR, the proton has to flip its spin from lower energy level to the higher energy level. That is, it has to change its spin from up to down. If the induced magnetic field opposes the applied magnetic field, the stronger magnetic field required to flip the proton. The proton is then said to be shielded, and the absorption spectra is shifted to upfield. Electron releasing substances shields the protons. If the induced magnetic field reinforces the applied magnetic field, the small external field is required to flip the spin of the proton. Each proton is said to be de-shielded, and the absorption spectra are shifted towards downfield. Electron withdrawing substances de-shields the protons. The effective magnetic field at the nucleus then is expressed in terms of externally applied field B naught by the expression as B equals B naught 1 minus sigma, where sigma is called the shielding factor or screening factor. The factor sigma is very small, typically 10 power minus 5 for protons and less than 10 power minus 3 for other nuclei. Differently situated proton in a molecule may be magnetically non-equivalent and comes successfully into resonance as the field is changed by the sweep coils. These differences in positions of resonance are called chemical shifts. This we have already seen somewhere here. I have repeated. Okay, I'll skip this one. This slide already shown earlier. Because of the shielding and de-shielding, we will get different signals in NMR spectra. Shielding shifts the absorption upfield and de-shielding shifts the absorption downfield in NMR spectra. This is lowest delta values, and de-shielding will be highest delta values as shown in the figure. So shielding shows the lowest delta values as shown in the figure, and de-shielding is towards the high delta values. Such a shifts in NMR spectra arise due to shielding and de-shielding of protons is called a chemical shift. TMS is used as a reference and its chemical formula is SiCH3 4. Measurement of chemical shift. Chemical shift is measured in frequency unit called as Hertz. Most of the routine instruments operate at 60, 80, 100 MHz. More sophisticated instrument operates as high as 600 MHz. So this is somewhat here. So more than 300 MHz and 60 MHz. The chemical shift recorded in the heads may vary with the spectrometer. To avoid this complication, the chemical shift values are expressed in terms of delta or tau scale, which are independent of field strength. Chemical shift in delta scale is expressed in parts per million. So chemical shift, which is measured in delta scale, which is equal to frequency of the sample minus frequency of TMS in hertz divided by frequency of instrument in megahertz. 1 megahertz is nothing but 10 power 6 ppm. So this is expressed in terms of the formula del equals new sample minus new TMS divided by new instrument times 10 power 6 ppm. So in practice, the chemical shift is usually indicated by a symbol delta, which is defined in terms of the standard reference as given by this expression. So chemical shift, which is defined as shift downfield from TMS in hertz divided by spectrometer frequency in megahertz. So there are two scales. One is about 60 megahertz, another one is around 300 megahertz. The NMR spectra are displayed as a plot of the applied radio frequency versus the absorption. The applied frequency decreases from left to right. Thus, the left side of the plot is the low field, down field, or de-shielded side, and the right side of the plot is high field, that is upfield or shielded side. The position on the plot at which the nuclei absorbs is called the chemical shift. Since this has an arbitrary value, a standard point must be used. The two most common standards are, this is R, TMS, Tetraethylsilane, SiCH3,4, which has been assigned a chemical shift of 0, and CdCl3, deuterochloroform, which has a chemical shift of 7.26 for proton NMR and 77 for carbon 13 NMR. The scale is commonly expressed as parts per million, which is independently of the spectrometer frequency. This scale is the delta scale. So this is what explained. One is higher field, another one is low field. And shielded field always will go with high field, and down field, de-shielded field moves only towards the low field. And intensity versus ppm is given, and this is the reference position. This is nothing but TMS signal. Factors affecting the chemical shifts: electronegativity and inductivity effect. Electronegative group attached to CH system decreases the electron density around the proton, and there is a less shielding, thus chemical shift increases. Magnetic anisotropy, hydrogen bonding. The first one is inductive shift. In NMR spectroscopy, an inductive shift refers to the change in the chemical shift caused by the electronegativity of substituents or functional groups, which can either increase downfield shift or de-shielding, or decrease upfield shift or shielding the electron density around the nucleus, thus affecting its resonance frequency. Anisotropy effect. The generated magnetic field is distributed non-uniformly at different regions, then it is called anisotropic effect. Anisotropic effects in chemical shift, particularly in NMR spectroscopy, arise from the non-uniform magnetic field induced by pi electrons in molecules like benzene and acetylene, leading to shielding or de-shielding of nearby protons. This is observed in the case of alkenes and alkynes. Hydrogen bonding. Hydrogen bonding affects chemical shifts in NMR spectroscopy, causing protons involved in hydrogen bonding, like OH or NH groups, to exhibit a broad range of chemical shifts, typically downfield lower ppm values. Due to deshielding, that is, the proton's magnetic environment becomes less shielded, causing its resonant frequency to shift downfield. The extent of hydrogen bonding and therefore the chemical shift can be influenced by factors like solvation, acidity, concentration, and temperature. Electron density. The presence of electrons around the nucleus creates a shielding effect, influencing the magnetic field experienced by that nucleus. Solvent effects. The solvent used in the NMR experiment can also influence the chemical shift, as different solvents can interact with the sample in different ways. Temperature effect. The temperature can affect hydrogen bonding and other interactions, which can in turn influence the chemical shift. Concentration. The concentration of the sample can also affect the chemical shift, especially for molecules that can form hydrogen bonds or other intermolecular interactions.